In this set of slides, we'll talk about the paired samples t-test. And the paired samples t-test can be used when the independence assumption is specifically violated in a special way such that the data are analyzed in pairs. We said, imagine you have two groups of people, say a group of Yankee fans and a group of Red Sox fans, and you wanted to see if the mean happiness level was different between those two groups. You could take the mean of group one, which we said was something like 65, and you could take the mean of group two, which we said was something like 61. And the difference between these, if this is actually 61.1, so the difference between the means was 3.9. And I ask you to write this down. Remember that the difference between the means is 3.9. But another way to think about this is if the study is designed in such a way that you have, say, pre and post elements, or elements that are somehow uniquely paired to each other, what you can do is look at the difference within each pair. This person went down 5. This person went down 5. This person went down 5. This person went down 2, and so on. Now, we saw that when you ran these data as an independent samples t-test, it was not statistically significant. There's no evidence that anything was going on. But if you look at the data the way they should be looked at, when you see the pairs, what do you notice? Well, every single person went down. So just from common sense, this must be statistically significant. Whatever I did to these people, whatever noxious stimulus I applied to them, it caused them to all go down. Now, if I had done something that was useless or didn't have an effect, what would you expect to see in this picture? Well, Tibor, I would expect to see a set of just perfectly parallel lines, right? Every person would stay exactly the same. Well, that would be a little bit too neat. Some people are just going to go up and down a little bit randomly. So we have 12 people here. You would expect about 6 people to go up, 6 people to go down. The ups and downs would sort of cancel each other out. And the difference that each person has, some would be up, some would be down. On the average, the difference would be 0, right? The average of the differences would be 0. But look at these differences here. 5, 5, 5, 2, 3, 5, 7. No, sorry, 5, 3. Every single person goes down. And so when we analyze these data, we need to not look at what is the mean of each group. Don't look sort of down each column and say, what is the mean of each group? But calculate the differences and say, what is the mean of the differences? And we're going to see something very interesting when we do this. Remember, the difference between the two means is 3.9. And I'm going to show you something very cool. When we analyze these data correctly, we run what's called a paired t-test because these are pairs. So the paired samples t-test, in Stata, you run it like this. This is a typo. Microsoft autocorrects t-test. It puts a hyphen in there. But in Stata, we have to be very careful with our code, with our syntax. The language we speak to the program has to be perfect. T-test, and then you list your two variables. One is called pre, one is called post, double equal sign, and here's the results that we get. Now, the pre, we saw it was 65. The post was 61. And that difference is 3.9. So when we think about the T statistic, remember what T is. T is a ratio of signal to noise, or it's the difference that we observe relative to how much things would bounce around by chance alone. This 3.9, I got excited, my voice cracked. The 3.9 in the paired t-test is the same. The numerator is the same. But what's going to be different is the denominator. When we run this paired sample t-test, look at T. T is really big. What would you expect to get for T if the null was true? If the two groups are equal, pre and post, you would expect to get 0. This is not 0. This is way out there. This is 9 standard errors away from 0. And 9 standard errors away from 0 is statistically significant. It's odd. It's rare. So when we run the paired t-test, there is a significant decrease of 3.9. The p-value is very small. It's less than 0.001. And we can look at that confidence interval and see that this confidence interval is pretty precise. We are 95% confident that on the average, after we do something to these people, say give them a stats quiz, their happiness declines on the average somewhere between 3 and 4.7. There is evidence that this is statistically significant. Now, how could this be? How could 3.9 be meaningful in this context, but when it's run as an independent test, how could 3.9 be unremarkable or not statistically significant? And it's due to the denominator of that T statistic. It's due to this idea of what is the signal that we're seeing relative to that random noise or that bouncing around. And I'll see if I can explain this to you on the next slide. The way that a paired t-test works is that it calculates the difference between the two measures for each person. So we can think about, just say the difference is how much you changed. You went down 5 or 3 or 2 or whatever it is. And then we calculate the average of the differences. And you might see this marked as D bar, the average of the differences. And then you calculate the standard deviation, not of the individual values, but of the differences. So in the T statistic, we use the differences. And when you look at how much people are relative to the mean of their group versus how much people are relative to the mean change, you see something very interesting. This might help to visualize it. When we ran this as an independent samples t-test, we said we had group 1 and we compared it to group 2. But when we look at things as independent, we lose the idea that this person right here, remember this person? Very happy person, 85 is their happiness. You can do a lot of things to this person. You might make them unhappier, but you're not really going to make them unhappy. Even when you do whatever we did to them, they go down, but they're still in general a happy person. They have a happy disposition. This person down here, who is, where are they on here? This one right here, number 11. This person's miserable all the time. You could give these people puppies and they're like, oh, great, a puppy. I'm still a 47. When we do something painful or noxious or unpleasant to them, they go down, like everyone goes down, and they're still sort of living in miserable town. But if you think about this, when we calculate that T statistic, we look at, here's the difference between the two means, 3.9. And you have to look at that difference in the context of the standard deviation of the groups. What does a change of 3.9 look like when happiness ranges all the way from 45 to 85? 3.9 doesn't look that big. It's not that remarkable. It sort of gets lost or swamped in just this wide range that things take. If you tilt your head all the way to the right, you can draw a normal curve on top of this box plot. It looks something like this. See that? And you can draw a normal curve on top of this box plot. It might look something like this. And when you see that, you really get a sense of how much overlap there is. 3.9 is not remarkable. However, when you think about these differences, 5, 5, 5, 2, 3, 5, what is the spread of those differences? This so-called the standard deviation of those differences. It's not very spread out. It's a bunch of 2s and 3s and 5s. And how does 3.9 look relative to that tiny little range of a bunch of 3s and 5s? 3.9 looks really big. 3.9 looks really big. And so that's why in the T statistic, when you use the denominator of the differences, we see that it's statistically significant. We'll explore this a little bit more, and we will talk about how do I know if my test should be independent or if it should be paired. And we'll cover that in the next set of slides.